Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am super happy to have Liz Jensen with us today. Hello, Liz.
Frank, thank you so much for inviting me.
Well, thank you so much for agreeing to talk about your very lovely APJ article, which we'll get to. And Liz, what's your geolocation? Where are you at?
I am physically located in the Houston area.
Okay.
Yeah.
It is April 3rd. It's spring, so there must be some battle going on between the Gulf and the North and the weather.
Yes, unfortunately, we fairly expect it to arrive around the time the eclipse does.
Oh no! Oh no! That's right. We're only
Yes.
about 5 days out or so from that. Oh
Yeah.
no!
Across the entire state. Like, I don't know that anyone's going to be safe.
Oh no! Well,
Yeah.
we'll see something.
Yeah.
I'm
Yeah.
in Phoenix. I'm in Phoenix. We'll probably be clear in some, but we won't get the total. We get like 50 or 60% or something like that. So, it's better than nothing, but it's not as cool as a total.
Yeah.
Very
Yeah. I mean, even if you can't see the total, you can feel it. It's
You'll
just
feel
got
it.
this
You'll feel the
completely.
drop and the general
Yeah.
little bit darkening, and so it'll still be cool. It'll still be
Yeah.
cool.
Yeah.
Very nice. Very nice. And Liz, what do you like to do for research?
Oh, so research, I would say that my primary interest would be safety.
Okay.
So in this case, it would be planetary safety. And what I've been working for a very long time is space weather applications to my research.
Cool.
So we're, looking into how to predict and observe coronal mass ejections whenever they're
Uh-huh.
coming to the Earth and
Uh-huh.
disturbing the geospace and causing all kinds of currents in the ionosphere and all the effects from that.
Right. Very
Yeah,
cool. Very
yeah.
cool. And that is going to bring us to this very awesome APJ article. Whoops. It is open access, people. It's the open access era. You can go grab a copy for free. Go get one. The hunt for perpendicular magnetic field measurements in plasma. And Liz, take us away.
All right. Um, let's see. So, first of all, I'd like to thank my co-authors, Professor Jamasina Simpson. She's in Utah at University of Utah, and one of her grad students, Yasser Ramani. He's helped us out with this work. And it was wonderful working with these two folks. And I
Cool.
would also like to thank a couple more people. I would like to thank the editors at AppJ because they funded publishing this particular article.
Ah,
And I would also like to thank our reviewer on the article, whoever that person is, because they
huh.
were excellent. I absolutely appreciate the feedback that they did because it made it so much better.
Nice, nice. Great shout outs.
Yeah. Yeah, it takes a team. So, all right. Well, so this work, what it did is look at a overlooked plasma wave mode. So,
Okay.
yeah. So what happens is that whenever a radio wave is propagating through a plasma, it does it, and yes, the wave action. We're going to be talking about waves. And it will do it in different modes. And so what we're most familiar with are what I call the ordinary mode and the RCP and LCP mode.
Okay.
Now, one of the issues that come, so there's two things that you need to know about this. The first thing is that we are talking about wave frequencies, or radio waves,
Okay.
are at higher frequencies than the plasma frequency, the cyclotron frequency, the
Mhm.
upper hybrid frequency. So this is in the high frequency regime.
Yes.
So that's what all these equations apply to, all the assumptions that we built into them. You need to, if you want to apply this to other regimes, you got to go back to first principles.
Yes.
So that's the first thing I want to make understood. The
Cool.
other thing is that whenever I use the terms O mode and X mode and RCP and LCP mode, they use the same terms in the ionosphere for different phenomena. So
Okay.
it gets confusing very fast. And
Okay.
so I built into table 1 specifically what I am talking about.
Okay, that's
And
what
yeah, and so this is where we get into the animated GIFs and
okay. So we're going to show some animations here on RCP, O, and X modes, and these are the dispersion relations. So let's take a look at what some of those animations. So these are value add to the paper. They're not in.
yeah.
Stop share. Let's go ahead and do a screen share on this one. And let's go and we'll start with the first one.
So the most commonly known modes relative to measuring the magnetic field is the Faraday rotation phenomenon. And that occurs because of the RCP and LCP modes. So what's important that you see in this figure is that the blue and red lines are your electric field amplitudes.
Okay.
And the direction of the magnetic field in this plot is along the line of sight.
Okay. All right.
And so what happens is that the RCP wave has a different phase velocity than the LCP wave, and that is an effect of the magnetic field. And so what happens in this particular configuration is that, let's say you are transmitting a signal that's polarized at 0 degrees. See the dashed lines there at the end?
Yes.
So it's starting on the horizontal axis there. And but by the time it reaches the end, it's at a completely different angle, and that's shown by the asterisk plotted on the horizontal axis. So you could think of so you could think that you're transmitting at 0 and your antenna is located, you got a cross dipole antenna and it's located where those dashes are.
Okay, I'm with you.
And so what happens is that the phase velocity of the RCP is a little bit more fast than the LCP, and so you get this net rotation.
Yeah.
And
okay.
yeah, and it's present even if your transmitted signal is elliptically polarized. So I use this technique with spacecraft that were not designed to transmit linear polarization. They leaked. So you have the cross dipole leakage, and that's what we used, is that 10% of opposite polarization in order to make these Faraday rotation measurements.
Very cool.
Yeah.
Okay.
So let's go back to the table and or maybe let me finish going through the animated GIFs and then we can go back to the table. So the important thing to know about radio waves whenever they're propagating through a plasma is that you can have think about a linearly polarized wave.
Okay.
It is all made up of components. If you have equal amplitude right and left-handed components, whenever they're summed together, you end up with a linear polarization.
Okay.
So what's deciding these components is the magnetic field direction. And so if the magnetic field direction is along the line of propagation, then what you're going to get is this effect in the RCP and LCP components of that. Even if it's elliptically polarized or linearly polarized, you're going to get these components traveling at different phase velocities. The property is called circular birefringence.
Cool. Good.
Now, whenever people do all their calculations relative to total electron content, this is very common in the ionosphere. I've done it with the solar corona. People will do it for radio astronomy with the dispersion relations on your pulsars.
Yep.
They all assume that phase, the phase change that manifests in the frequency is an O mode wave. They don't assume any magnetic field influence whatsoever.
Okay.
Now let's go to the O mode wave and I'll show you what the issue is.
Ooh.
So in this case, you see the propagation direction and our magnetic field is perpendicular to the propagation direction.
Okay.
And the electric field is oriented in the same direction as the magnetic field. So what happens is that there's no magnetic field influence to this particular solution. And so you have a linearly polarized wave.
Okay.
So
Uh-huh.
whenever you take those relations for how electromagnetic radiation propagates through the plasma, the magnetic field determines the nature of the wave. So even though if you have an oblique magnetic field where part of it, so the electric field is partially up, but it's tilted somewhat forward, you're
Uh-huh.
going to end up with Faraday rotation in addition to this linear component. So it's it's starting to get a lot more complicated
Yep.
what you have coming out of the system.
Okay.
And then what happens whenever it starts to rotate? The amplitude in the O is going to start to go down, but then you still have a little bit of a magnetic, you have a bit of an electric field off of the magnetic field. And
Yeah.
that's the X mode case.
Okay.
So
Okay.
so you take your plasma propagation, and if you have an oblique magnetic field, it is propagating in multiple simultaneous components.
Yes. Yes. Yes.
Yeah. Okay, so now let's look at the X mode.
Okay. I'm with you here. Okay.
Okay, now this one was difficult to visualize. And so part of the problem was that it is rotating along that propagation path. So you can
Oh,
see
you can see it.
propagation. Yeah. So
Okay.
you can see the propagation direction increasing.
Cool.
Yeah. And then of course magnetic field is perpendicular. We put in the Z direction. And another thing to know about this particular wave mode is that it's elliptically polarized. Anyways, what?
No, good. I'm with you. Uh-huh.
You're with, okay.
Uh-huh.
Feel free to ask me questions.
Yeah, yeah.
I'm
No,
like hitting lecture mode here.
no. I'm engaging. We're good. I'm following you.
Okay. Yeah. Okay. So if you have an oblique magnetic field in your background and your line of sight, your radio wave is propagating, and it has a perpendicular component, it has a component in the electric field of your radio wave has a component along that magnetic field,
Okay.
and then it's got one that's perpendicular where the E field is going up and down.
Okay.
And then you have part of it perpendicular in the other direction. You've got a complicated propagating wave.
Yes.
So whenever you look at those figures for linear propagation of a wave going through, and we're going to start rotating it, and this is Faraday rotation,
Uh-huh.
it's a sum of a number of these solutions, and they all have left out the X mode.
Ooh.
Yeah.
Okay.
Yeah. It
Okay.
so and it's a secondary
Nice.
mode.
Yeah.
And I think that because it's been a while, it's taken technology to catch up to the point that you could actually detect its effect on the signal, that it's time to start looking closer at this. So in those dispersion relation calculations using pulsars in radio astronomy,
Yes.
they're going to have a component of the magnetic field in their measurements.
Yes.
And so that's what I'm going to get to.
Cool. Okay.
Yeah. So we can go back to the paper now.
I think this was effectively visualized. I think if you just watch it for a while, you'll get the point. So it's very good.
Yeah.
Good job.
Yeah.
Okay. Let's go back to those dispersion relations. And boom, let's go. Okay. So here's our dispersions.
Okay. So so you can see the RCP LCP mode. See how it's plus or minus the cyclotron frequency in the denominator there?
Yep.
Yeah. So that's the circular birefringent property whenever the magnetic field's aligned with the propagation path.
Yes.
And then in the X mode, you see how the cyclotron frequency is squared in the denominator there?
Yep.
What that means is that you can get the magnitude of the magnetic field strength in the perpendicular, but you're not going to get the direction. So whenever if you combine your measurements so whenever you combine these all together, you can get like a cone solution for the magnetic field. You
Okay.
know, if it was this direction or that direction, by how much, but you don't know the exact vector.
Yes. Okay. Okay.
Yeah. All right.
Very good.
So the question comes
Okay.
in is,
Uh-huh.
uh, what does that mean for the measurements that we're currently taking, and what does that mean for the measurements we could be taking?
Good.
And so let's go to the next figure.
Okay. We've got some discussion of our perpendicular B mode here.
Oh, wait. Equation 7.
Yeah, I was gonna say.
Yeah, let's take a quick look at equation 7.
Sure.
So everybody's familiar with, let's scroll up just a, no, perfect. It's perfect. Everybody's familiar with equation 6 and
Yes.
Faraday rotation. And so what I show is this alternative way of deriving the Faraday rotation equation. And then I go in to say, okay, we're going to take this alternative approach and we're going to derive equation 7.
Yeah.
And so now that I've taken this alternative approach to solving these equations, I need to test to see if this is any good.
Right.
Did I capture the physics or not? And
Sure.
there's a funny story there if you want to hear it.
I want to hear it.
So relative to the general equations that began, which is the phase and group velocities and combining them together
Yes.
to find your arriving phase differences.
Mhm.
I got to those because I was on a 10-day hike
Okay.
and we were going, I don't know, 70, 80 miles or something like that over those 10 days. And
Right.
I brought I brought some notes with me so that whenever I was relaxing, I could just sit there and play with Maxwell's equations.
Cool. Cool. What else would one do on a hike? It's awesome.
Yeah, it was with the scouts with my daughter, and
Cool.
so while they're figuring out, you know, where are we going next and all those kind of details, I'm letting them do their thing. I'm not interfering, and you know, just scratching away. So
Cool.
that
Cool.
was fun.
Very nice. I love it. I love it. So where
All
was it?
right.
What part of what were you hiking? Like Appalachian Trail or something? Or
No. So there's a Scouts BSA. They opened up to females,
oh,
and
okay.
they've
Yeah.
got the Philmont Scout Ranch, and
Okay.
so it's in New Mexico, and just fabulous experience. You
Yeah.
know, you you challenge yourself and you develop, you know, the self-reliance and confidence and stuff. It's really
Very
good,
cool. Very cool.
really good for the kids.
So
Yeah.
New Mexico, very good. High desert. Okay. Plateau.
So we saw snow while we were up there.
Uh-huh.
And coming from Texas, that was a bit of a shock.
What is this stuff? What is this stuff? No, I was just
Pretty
in,
much.
yeah, no, I was
Pretty
just in
much.
Santa Fe last week and they were still getting snow. So
They need to come visit Texas in April.
yeah,
All
see,
right. Yeah.
cool.
Yeah. All
Uh,
right. So let's go okay. So let's go to figure 1.
Okay, so figure 1. So now we're gonna test this Appleton heart tree. Bang.
Okay. So the first challenge was is checking how useful this is.
Yes.
You good? Okay. So we used it to calculate what the O mode would be, and then we calculated what the X mode would be under the conditions that are provided in the bottom of the figure. So 477 megahertz
Yep.
for the signal, and plasma frequency and cyclotron frequency
Okay.
are lower, obviously.
Okay.
So so then we look at how that the Appleton-Hartree equation is your fundamental plasma propagation equation, but it's hefty, and I'll show later in the paper why we needed to simplify it for applications to physics calculations.
Okay.
And so, but first, we needed to compare how do these equations develop error. So as we propagated, you can see it's only about 12 meters, 13 meters.
Yeah.
Differences in degrees already started developing between the Appleton-Hartree solution and the paper solution.
Okay.
And,
Okay.
you know, it's on order of 10 to the negative 7 or 10 to the negative
But
4. That,
yeah. Uh-huh.
yeah, those are, yeah, thank you. Those are the Taylor mode assumptions built in there. You're gonna, yeah, they're not exact.
Right.
And so, so whenever you are looking at Faraday rotation,
Okay.
the measurables develop with a coherent structure over an extended period of extended spatial dimension. So you need a good line in space, sized line, and we're talking on the order of megameters or longer
Right.
of a coherent structure in order to get get something measurable, something that you can study out of it.
Okay.
And so if we scroll down to the was it figure 3? I think it was figure 3.
Let's go down 8, 9.
Not that one, it's the next one, I believe.
DT.
That one. Yeah.
This one is your CMEs. Okay.
Yeah. Yeah. So here's kind of what I'm used to working with, is this kind of a baseline, is that you have a transmitter on the opposite side of the sun from the Earth. So here I show a idealized situation. This is all out of a 3D MHD model.
Cool. Very good.
And yeah. And so so this is a 3D MHD model of a CME that erupted May 13th, 2005. And we put in a transmitter and a receiver on either side of it.
Got
And
it. Okay. Okay.
and then that's when we started running into trouble with Appleton-Hartree. So I only took the 1 times 10 to the 10 meters that are shown by the red triangles.
Okay.
For the
Right.
testing of this equation and equation 7.
Okay.
So I took the average density you see there, the average magnetic field across that particular distance to do the test for our equations.
Cool.
But
Okay.
this gives you an idea of the scale size of what we're talking about to manifest features, and what kind of densities and magnetic fields
Right.
that went into this test. But it will apply to the ionosphere, which naturally will have a larger magnetic field and variable density. It depends on where you're looking, but
Absolutely.
and
Okay.
yeah, so this applies to you can use it for different regions, but I wanted to show where our numbers came from for our test.
Good.
Yeah.
Good. Okay.
Yeah. Okay, so let's scroll up to figure 2.
Okay. Okay, got that one. Okay, figure 2.
I really like to talk in pictures
Pictures
to explain where those parameters in the equations came from.
Okay.
Okay, so here's figure 2, and here we are testing it out. Now, what I did was we are looking at a developing phase difference.
Yes.
Over an extended line of sight. So between the Appleton-Hartree and the calculation 7 and equation 7, or the O-mode version, you're going to see that there's a significant difference in the actual phase angle. Now, with time, as your plasma conditions change, how they change with time is what we're looking at.
Yes.
So while the actual delta in phase angle is different, well, the actual delta in phase angle is going to be different. How they step in time whenever we have changing plasma conditions is going to be the same. is what we show. Okay, so
Cool. Okay.
so the way this manifests is shown here, and it's in a frequency. So you can see radians per second in the second row and in the fourth row.
Mm-hmm. Yes.
Yeah. And so so we did a couple of tests. The first test was we had the plasma frequency, we had it step down by a megahertz
Uh-huh.
for 10 seconds, and then we had it step up for 10 seconds. And then
up. Huh?
yeah. And then throughout that time, we had the cyclotron frequency just keep on descending. We could have left it flat. It's just as long as the plasma conditions change.
Yes, that's the key here. Okay, I'm good.
Yeah.
Mhm.
So, so in the second row, you can see what happens is that the change in that frequency, the radians per second,
Bang.
is negative. So the way this manifests in spacecraft signals is that so we have a bit of an easier time in some ways than radio astronomers because we have this narrow band signal with a lot of power to it.
Yes.
And yeah, and so you can actually see that narrowband signal change in frequency with time. And you know it's not changing because this is your spacecraft. It's not Doppler. Your spacecraft can sit there fixed and, you know, no Doppler motion whatsoever. And you can
Okay.
see that narrow 1 to 10 hertz frequency bandwidth just shift in frequency.
Okay.
And most of it is because of the changing plasma
Condition. Yeah.
yeah. And so it's really nice
Okay.
to use that effect for tracking, is your plasma decreasing or is it increasing? So what you can
Yes.
see is that if it's decreasing, it's negative. If it's increasing, it's positive.
Okay. Yes.
Yeah.
Yes.
So you know what your center frequency is. If it's negative, you're losing, your plasma density is going down. And if it's positive, plasma density is going up.
Strictly on the slope. Okay. Okay.
Yeah. Okay, so now we go and we look at the X mode. And this is why I said it's kind of a secondary effect. And so in the second case, which is shown in rows 3 and 4,
Yes.
we had the plasma frequency step down.
Yes.
And so that's going to make it negative. So you can see the radians per second, it's all negative. It never goes positive. And then we had the cyclotron frequency step down and then step up.
Step up. Yep. Okay.
So the way to look at it is that the plasma frequency, it is going to just constantly be negative. And then any slope on top of that is going to be the X mode.
Oh, I get you. Okay. I get
Yeah.
you. Yeah.
And so,
Cool.
yeah, so the triangles you'll see are very straight, whereas the blue line is kind of bumpy.
Wiggly a little bit there. Mm-hmm.
That's because the Appleton heart tree is breaking down on us. The floating point processor can't deal with it.
Ooh, so
it's
beyond the floating point range of the chosen arithmetic.
Yeah.
It'll start 8 double precision, something like that.
Yeah, well, I mean, you can, go at it with different strategies, but this is why the equation is useful.
Got it.
Is that you can use it on these long distances. You can use it for 1 times 10 to the 11 or 2 times 10 to the 11 meters.
Nice. Okay.
Whatever your challenging circumstances are. Appleton heart tree becomes very hard to work with, and this equation will do it for you.
Nice.
So, so for comparison, the orange line, or I guess it was supposed to be red, but anyways, that is your O mode solution. So that's the O mode component, and it's not changing at all because it's tied to the plasma frequency, no magnetic field effect.
Yes.
And then the blue line with the red triangle shows the effect of the X mode.
Mhm.
So it's
Okay.
small,
Yes.
but it's present.
Cool. Okay.
Yeah.
Mm,
And so
built up about.
the
Yeah. Okay.
question comes in is how significant is this?
Okay.
So
Yeah. Fair.
yeah. So depending on your frequency, depending on your viewing conditions, etc., how significant is this? And what it comes back to is your total electron content measurements. One
And
of the befuddling problems with it, and I've seen this with I was using Cassini to do solar observing with the Deep Space Network.
yes.
And we were watching Cassini from whenever it rose above the horizon until it set on the other horizon. We
Okay.
had a good chunk of time observing. And I could never clean up the data enough to use it whenever it was on the horizon.
Okay.
And for the longest time, I thought that might be an effect of warping of the dish. Like I wasn't quite capturing,
Okay.
how well that 30-meter dish was handling up there. But with this effect, I think that
Got it.
a good chunk of the noise was the fact that whenever you're looking off towards the horizon, the Earth's magnetic field's coming up and it's perpendicular. So you have this
Yes.
strong magnetic field perpendicular, and you have this extended density because in the horizon, the least amount of density is whenever you're looking zenith, and then whenever you're looking through the horizon, it's the longest.
Right.
And so
Darkening, so to speak.
yeah, so I started kind of asking myself, why is this so far off? And another issue that would pop up is, why were the error bars on the ranging? So ranging uses the group velocity, and then I was comparing those numbers to the frequency fluctations to obtain
Okay.
the phase velocity,
Okay.
and they were averaging. So the phase velocity, let's just say it's just this curve. It would make this bowl shape, frankly. So it was just this curve, but the ranging would be scattered around that curve significantly.
Okay.
And so
Okay.
it struck me that whatever effect I was looking at, it was present in both the group and phase velocities. So that was one of the things that I was kind of looking at while I was on my hike. What does the magnetic field come into play on both?
Yeah. Okay.
Yeah. And so what this means is that there are two places where you could expect a fairly strong perpendicular magnetic field in current observations, let's say through the ionosphere. And that would be if you're looking off towards the horizon.
Okay.
And then also the auroral oval. The auroral oval is a very dynamic place with the currents. And wherever you have a curved magnetic field, you will have a current, because magnetic fields want to be straight. Well, okay. How do we put this? So magnetic fields are force solutions for what the particles are doing. I keep on telling people magnetic field lines are imaginary, but they're very useful.
Okay. 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 That's good.
Imaginary
Like
condition.
that. Yeah. Yeah. I like that. That's good. Okay.
Yeah. So, whenever your field lines are curved, there are currents present, and what the currents are trying to do is to straighten
Right
the
now.
magnetic field lines. Yeah.
Yep.
And so in the auroral oval, where you got your very strong currents, you're going to have these curved magnetic field lines as well.
Yeah.
And so it's going to be strongly perpendicular.
Okay. Okay.
So, well,
Good.
how strongly kind of comes into the conditions. So is it, a matter of 1%, 10%?
Right.
Yeah.
Exactly.
Yeah.
For each of those.
So there's this broad application there. Another application is that in certain circumstances, such as the Cassini data set that I still have. Oh, I haven't introduced the other equations. Okay, so we need to scroll up a little bit to the equations where we isolate this effect. There we go, 8 and 9.
Mm-hmm.
Okay, so the question is, how do you isolate the component that's the O mode that has no magnetic field effect whatsoever from the component that has the perpendicular magnetic field in it? And I'm only looking at the case where the magnetic field is purely perpendicular to the propagation path. Whenever this is going to go into future work, whenever we talk about, where are we going? The oblique case may have some modification on this, but it's going to be minor.
Okay.
So that's my future work, is to find out what that minor component is. So in this pure perpendicular case, you can isolate the two effects. And so with and once again, I'm approaching this as a spacecraft person, is that I can have some spacecraft transmitting two frequencies.
Sure.
And so if you can identify unique frequencies and see those, those really narrowband signals shifting with frequency,
Yeah. Okay.
then the relative amount that they shift can be used to isolate the total electron content component from the perpendicular magnetic field weighted total electron content weighted component.
I did get it. Okay, very good. And just what is epsilon here in 8 and 9?
Permittivity of free space.
Okay, just checking.
Yeah.
Big scale.
So,
okay, very good. I followed that. Okay.
So for your natural sources, we're starting to look at what can you do? How can you apply this for a natural source? And so the pulsars have the dispersion relation, which, they have a range of frequencies to them. And is there a modification, say, of the curve or something like that? So we're starting to look at that.
Cool. Very cool.
All right. And so with two frequencies and you process them moderately different, you can isolate the two components. And so this is good for total electron content analysis with the ionosphere.
Cool.
There are some areas where it's very difficult to place a receiver. And so the data coming in for our models with the space weather prediction, can get some better coverage by enabling this.
Huh?
With respect to the magnetic field component, we went to see, can we pull that back out? And that's the purpose of the last figure. Yeah, so here's where things get challenging, and this is for everybody that works with remote sensing. Is that you end up using certain assumptions, and then you have to modify those. So it's an iterative process. And one of those things is that instead of looking at equation 11, let's look at equation 10 really quick, because that one's a little bit easier to walk you through. So what happens is that tentatively you can just integrate with time what your time integrated equation is, and then divide by the distance in order to get what your average density is. But there's an assumption in there, which is that the distribution in density is consistent across that line of sight. Yeah.
Yes.
And that's not always the case. I mean, we show in figure 3, that's not the case. And so And so whenever we go to test, can we pull back out the magnetic field and the density? We are applying this particular assumption, and everyone who works with remote sensing knows that you've got to be very careful how you handle those assumptions and what you're trying to pull out of them.
Right.
And so what can happen is that, for example, whenever I'm using Faraday rotation and I'm trying to figure out what the magnetic field strength is, if I'm not careful, I can get a magnetic field strength that's weaker than it should be because it occurred in an area of lower density.
Yeah, yeah. Uh-huh.
Yeah.
Mhm.
Yeah.
Kind of those
And so,
Mhm.
yeah. So you got to be very careful backing that stuff out. So then let's go to equation 4. Everything's perfectly ideal. We have this, perfect slab of plasma that's consistent in magnetic field and density throughout. Oh, figure 4.
Figure 4, sorry. I was gonna say, that sounds like a
Yeah, it's all good.
serious dream there. Okay, figure
There
4.
we go.
Here we go,
That's
solar
figure 4.
wind.
Okay, so slight correction.
Okay.
The axes on the top row are not plotted in time. They're just plotted by points. The correction somehow didn't get uploaded or something. But for getting the timing on these, because you're looking at differences, you have to subtract your first point from the second point. And so we started
Yeah.
the time at 2. And so take all those plots on the first row and shift them over 1.
Okay, I'm with you. Yep.
And then they'll be properly aligned in time. Okay. So what happens is that we were able to recover the density pretty well. And you can see that first term, total electron content. Here's what we got for TEC, numbers per meter squared. And then we said, okay, what is the density, assuming it's perfectly even?
Right.
And you can see what was input is the blue line, and what came out is the red triangles. We got our density back.
Cool. Okay, so that works.
Yeah. Now, one thing I should say is that we are using the Appleton-Hartree solutions.
Okay.
Because if we used our solutions, we'd just be backing out what we put in, which of course it's going to give us a perfect answer.
Well, that's lovely.
So the top right figure is wiggly because we got the Appleton-Hartree, floating point processor fun in the solution there. So anyways, there's our term, nice and isolated there. So it's the integration of NB perp squared ds. You can see that in the title. And so then we took that, said perfectly wonderful slab, everything's fine. Now, you can see we got our magnetic field back. And that the input you can see is this nice straight line. And then because we used Appleton-Hartree, the magnetic field, the red triangles are all wiggly.
Right, wiggling around that, but wiggling around it.
Yeah. And one other thing that I need to add is that you will see this in the code, because the code for producing these figures is available on Zenodo.
Yay!
Yay. And what you'll see in the code is that the total electron content that we put in is the original total electron content, because we wanted to show how it plotted relative to the input. If we use the total electron content that was calculated on the left side, you would have seen a perfectly displaced magnetic field magnitude. It would have been offset downward by, I don't know, like 0.01 Tesla, 0.01 times 10 to the negative 7 Tesla or something like that. It would have been displaced.
Shift.
So it would have retained the changes. It would have retained the shape, but the actual value would have been displaced one way or another.
Right. So
that's typical for this kind of calculation, because relative to using the phase relations to do your total electron content, you get the change in total electron content, but you need another data set in order to fix it, to know what the initial total electron content was to apply the change to.
Right, correct. Yeah, you need the baseline.
You need a baseline. Yeah. And so that's similar exactly similar kind of problem here. And so, so in this one, we grabbed the baseline from the input, but just to show here's
Sure.
how it
And it
plots.
recovers. Yes.
Yeah.
Cool.
But in the code, you can just uncomment one line and see how it goes if you go with the total electron constant solution. So, anyways.
There we go. You can check that out in the 2024 paper, where that code lives. Very cool. Very nice. All right.
Oh, one other thing with the code is that it's written in MATLAB, but MATLAB is, you know, kind of hard to get especially if you're on a restricted budget. So there's also a free version called Octave that's out there.
Oh, yes.
Yeah, and so it should run on Octave. I haven't actually tested it, but there are no commands in there that are unique to MATLAB, so it should run.
Okay, very nice.
Yeah.
Go check it out, people. Do it. Very cool. All righty. And that is that. And so, Liz, I want to thank you so much for walking us through this hunt.
Oh, so where do we go? One thing I wanted to also add is that there are other data sets out there of spacecraft with dual frequencies. So for example, I've got dual frequency Cassini data, I've got Magellan data. Those are the two that pop off the top of my head, but there's also other dual frequency Cassini data sets out there. Like there was one point in time where they did observations in S, which is 2 gigahertz, and X, which is 8 gigahertz bands through Saturn's ionosphere. So Cassini was on the opposite side of Saturn from the Earth, and so they sent the signal through Saturn's ionosphere to get measurements of density. Well, those measurements, if you reprocess those raw data points, and I double checked, they do still exist. So if you go and reprocess those data points with these equations, you could potentially pull out measurements of Saturn's ionosphere's magnetic field.
Very good.
And so this also has the potential to go back into archive data sets as long as it's raw data to go and pull these things out.
Right. Very cool.
Yep.
So are there plans to do that?
Proposing.
There were plans then.
Yeah. I mean, you know, likelihood of getting selected is worse than playing Keno, so I have no idea.
Yeah, who knows on those things, but there are plans.
Yeah, there are plans.
Very cool. Very cool. Well, I really look forward to seeing this develop over the next couple of years. I think it'd be really fantastic to pull out these perpendicular B fields. Be very cool.
Yeah. And I'm a big fan of AppJ, so you know, y'all are gonna get a number of my papers these days.
We love them.
Y'all did great. Y'all are just so fantastic.
There you go. Well, thank you for the compliment. Appreciate it.
Yeah.
And that will do. And I hope so. Thank you once again, Liz, for walking us through your very lovely article. And
thank you, Frank, for inviting me.
Yeah, sure. And everyone, I hope this made your astronomy day, especially your B field astronomy day, just a little bit better. And we will see you on the next one. Bye-bye.